First thing I wanted to talk to you about, well, some announcements, I guess, first before we begin. Homework 3 is due like right now-ish, so hopefully you sent that to me already. Homework 4 has been posted, actually posted on Tuesday, but we're going to talk today after we get through our topic, which is actually directly related to the final homework assignment. And that will be due on the last day of class, 2 weeks from today, as well as your projects / presentations, which hopefully you're working on those. Hopefully those are going well. And that's really about it. So I will try and get homework 3 graded as soon as possible, ideally tomorrow, but so yeah. The first thing that I wanted to talk to you about today, before we actually hop into our topic, as I promised on Tuesday, the new top 500 list came out this week. And so I wanted to just spend a few minutes talking about the top 500. Here is the top 5 on the list. And I know we first talked about the list towards the beginning of class several weeks ago, but if you did a diff between the top 5 that you see here and the top 5 that you saw from last November, you wouldn't see any changes. This is quite literally exactly the same as it was in November. So kind of not particularly exciting. However, there are some things we're talking about in relation to this list. The biggest change, the computer with the largest change, there was actually a new entry at number 7 on this list. So I cut it off at number 5, but there's a new entry at number 7 on this list. The Shaheen 2 is what it's called. It's the largest supercomputer in the Middle East, so it's in Saudi Arabia, at one of the universities in Saudi Arabia, which has about 200,000 cores, and it clocked in at about 5.5 petaflops. So you can see that, compared to number 1, right, it's about a sixth, give or take, the speed of the number 1 fastest computer in the world. And also many, many fewer cores than the fastest computer in the world. In fact, a lot of people are speculating that that number 1 slot isn't going to go anywhere for a pretty long time. So it's a pretty steady drop off from number 1 even to number 7. We're at 5.5 petaflops, whereas number 5 is at 8.5. Number 1's at 33.8, which is just ridiculous to think about, right? And that was kind of, the story here. The story about the top 500 list this year wasn't, oh, hey, look at all the cool new stuff that's going on. It's, oh, hey, look at how much stuff hasn't really changed at all, which is becoming sort of a concerning trend. So, they printed some statistics that there were fewer new entries this year, this list, than ever before on the top 500. I think there were only 79 new entries on this list, mostly occurring towards the bottom, not towards the top. That number 7 was kind of the exception to the rule, right? And also, the systems on this list have the highest average age than any list in the past, which kind of implies that people aren't really making these things as much, right? They're not building newer computers as much as they used to, which are kind of interesting trends. Yeah. That's a good question. I actually don't know. I mean, can you look up statistics about, are there publicly available stats on that particular cluster? It could be on the list. I haven't examined every entry that's on this list. To be on the list, you actually have to submit it. So there's very likely could be, and probably are, systems in the wild that could be on this list but aren't, just because whoever owns them doesn't want that information to be out there in the world, right? So yeah.
I was reading up on this presentation. This says supercomputer from so 80% of supercomputers in the world are not on this list.
Oh, I see.
Are not qualified.
They're running a different benchmark then?
Yeah.
Or not running any benchmarks then? So this is the top 500 of 20% of the world's supercomputers then is basically the gist of it, I guess.
It's 15, so 20%.
Yeah, run LinPack. Well, I mean, part of that's probably, if you don't think you're going to do well on the list, then that's sort of a disincentive to try, right? For a lot of people. I think the trend that I would expect on this list are that the ones towards the top are probably truly the best in the world, or at least very close to the best in the world. And as you fall down the list, there are more likely to be gaps and holes, because there's just not a lot of prestige of being number 327th on the list, right? Like, who cares who goes down that far? Being in the top 10, that's something you can brag about. That's something you can put on your resume. So, yeah, there definitely are political things involved. There definitely are other factors here than just pure computing power involved. I thought the one about Saudi Arabia was particularly interesting, though. They're starting to show a lot more interest in the high-performance computing realm. It was a specially designed Cray computer, I think, that they built out there to replace an older version that they had. So, anybody else have a chance to take a look at the list over last week? Like I said, there wasn't a whole lot of interesting stuff, but people expect this trend to continue. Fewer new computers being built. So performance is expected to kind of stagnate for the next few years, which is kind of concerning. I mean, for a while, it was just up across the board. And it's actually going to shrink the list down to some extent, because if number 1 doesn't go anywhere, well, number 500 is going to keep creeping up and creeping up. So the range that you see on this list is going to get smaller and smaller if this trend continues. And so it'll eventually kind of converge. I mean, they won't ever all be exactly the same, of course, right? But it's heading towards a convergence of sorts in terms of overall power, overall performance. Which is totally different. I mean, even this started happening, I guess, 2 or 3 years ago. The first time I taught this class was 2 or 3 years ago when the Milky Way just came out, and it was very big news for it to show up on the top of the list. I don't expect it to come out like that for another few years at least. So, cool. Any other questions, comments about the top 500 before we jump into our topic for today? All right, great. Well, then today's topic is one that's going to directly concern you for the 4th and final homework assignment. We're going to tackle the Nbody problem, which is a very, very famous problem in the realm of high-performance computing. So we're going to spend some time what the problem is, how is it defined, how do we compute it. We'll talk about a few different methods for computing this problem. And then we'll take a look at some code that actually implements this problem, and I'll turn you loose on the homework assignment. So the gist of this problem is I've got a whole bunch of objects in outer space. Move. I just want to know where they're going. So that's a very simple way of stating the problem. It's a pretty simple problem, right, to understand. I've got a whole bunch of stuff out in space. I want to know how it moves. That's very easy to grasp. But from a computational standpoint, that's where it really gets interesting. So many uses for this, not just stars and planets, but some other interesting uses that we'll talk about towards the end. Some interesting research papers written on different types of the Nbody problem. We'll focus mostly on planets, I guess. I'll probably just keep referring to planets. This is an old problem. Newton is credited with the first formulation of this problem in his famous work, the Principia, which was in, I forget which century off the top of my head, but many hundreds of years ago, which makes sense because one of the large factors of the Nbody problem is going to be gravity, right? Gravity is going to play a huge factor here. So Let's start to formulate this problem. First thing that we need to do, we have a set of n bodies where n could be, you know, as small or as large as we want it to be. For the purposes of this class, of course, we're going to be talking about very large numbers of bodies. And so let's start off with what we know about each of these things. So what do we need to know about these particular bodies in order to predict their motion? Somebody help me out? Yeah. We need to know their mass. Absolutely. So that's going to come into play. What else do we need to know? We need to know their position, their current position. So we'll have X, Y, and Z positions. What else do we need to know? Velocity. We need to know what's their current velocity. But velocity is not one directional, right? It's also typically broken down into X, Y, Z as well. So we'll represent it as 3 pieces. And that's really about it. We hit all the bases, right? We need to know how big these things are, where they are, and what direction they're currently moving in. There's some other constants, of course. Gravity is going to come into play here very shortly. But this is what we know. This is what we know. And actually, if you look at it, it's really 7 different values. 3 for position, velocity, and then the mass. So that's what we're dealing with. So how do we actually solve this problem then? It's a physics problem. I know this isn't a physics class, but the physics behind this is not particularly complex. So let's walk through it step by step real quickly. For each object, so we have, you know, I'm not going to draw a whole bunch up here. I'll just draw a few, right? For each object, what do we have to do? Let's just pick one and start with it. What do I need to do first? Have any physics buffs in here? I got a minor in physics, so I love this stuff. Yeah. Yep. We do need to calculate the forces, so that is definitely a step, but let's break that step down, and just calculating the forces is also a non-trivial process. Due to what, primarily? In this case?
Gravitation.
Gravity. So what do I need then to figure out those forces due to gravity? What do I need to know? What's that equation look like? Distance. So the very first thing I need to do is figure out what are these distances. Right? We need to compute the distances. That's based on these X, Y, Z positions, right? I can write the formulas out. Once I have the distances, then I can start to compute the gravitational force, which is this very famous equation, right? The 2 masses over the distance squared will give us, oh, I forgot the gravitational constant, of course. There it is. 2 masses over the distance squared times gravitational constant will give us the force due to gravity on a particular body, and it works in both directions, right? The same force that's acting on this is going to be the same force that's acting on this, just in the opposite direction, right? Okay. But we have to be careful, right? So what do I do next? I have these distances. I have these forces due to gravity, but I actually need the forces from each of these particular bodies, right? So I need the forces that are coming from here to here and the forces that are coming from here to here, right? Because both of those forces are acting on this particular body. If I had 500 planets up here, I would need to figure out 499 different forces that are acting on this particular planetary body, right? Kind of see how this problem is, how the size of this problem is going to start expanding. Once I have the forces, then what do I do? Once I aggregate all of those forces from every different direction, what do I do? What do I do next? Yeah. Acceleration. So we can do acceleration next. Compute the acceleration of our bodies, of our particular body. And then once I have the acceleration, it's a pretty easy conversion to figure out then the velocity, right, in each particular direction. And then finally, once I have the velocity, I can apply that velocity to my current position to give me the next position in space, right? So it's a pretty straightforward process, but a lot of steps. a lot of steps that we have to do, and a lot of steps that we have to aggregate across all of these particular bodies, right? I have a quick example showing this actually for 3 bodies that I loaded up on YouTube. This is just a 3, oops, I guess I need to refresh. This is just an example with 3 bodies, right? And you can see every time it places a white dot down, that's the computed position for a given time interval, right? So we're going to do this over some time interval t for each of these 3 bodies. And so you can see that the blue one, I can full screen this, maybe. Oops, I just broke it. Thanks, YouTube. Oh, crap. Did I just crash my computer? Wake up. Awesome. Fantastic. That's never happened. It is straight frozen. Excellent. Excellent.